Many scientists at the start of the story of quantum mechanics were very resistant to these new ideas, and they had very good reasons for resisting them. These ideas seemed to offer an explanation for observable phenomena, and there were no other good explanations. But they disagreed with the core ways we thought about the world. And as I said, it's important to understand that even many of the scientists involved really did not want the world to have to be described this way, including, for example, Max Planck. And Max Planck was initially very resistant to the ideas of quantum mechanics, even though he was the person who started it. Now, as the theory developed, as a good scientist, he eventually did come to accept it, but with great reluctance. And I expect we all know of many people who only believe what they want to believe, and there's possibly a moral lesson here. But the reluctance in the case of quantum mechanics to believing it is extremely understandable. The problem was not only that it struck at our whole way of thinking about the world. If this quantum theory was correct, it would mean we would have to completely rewrite physics. And any new scientific theory has got a very high hill to climb. It has to give exactly the same answers as the old theories, everywhere those old theories and previous models worked. And yet it also has to successfully describe the phenomena that we couldn't understand before. Now, the prior theories of mechanics, like Newton's laws, worked very well in a broad range of situations. Our models for light, similarly, were quite deep, and it achieved a remarkable unification of electricity and magnetism. Maxwell's equations from the 19th century are one of the major triumphs of 19th century physics. So how could we, in some sense, possibly throw away all these models, which also do work very well in certain domains and scales? How could we possibly come up with a new basis for all of these that was fundamentally different, but nonetheless gave the same answers everywhere they did? That requirement that any new quantum mechanical theory should also give results that correspond in these appropriate domains with the classical results is called the correspondence principle, by the way. Of course, it was also true, as we looked more deeply at these various phenomena in light and atoms, that there simply was no way we could explain them with our classical view. And those classical models would themselves lead to contradictions with observed reality. For example, as we discussed, when we would try to make a model of the atom with the electrons circling around some charged nucleus, like a satellite in orbit around the Earth, we meet major inconsistencies. Existing mechanics and electromagnetic theory, as I said, would predict that any such orbiting electron would constantly be emitting light. But atoms, for example, in their ground states, simply do not do that. The challenge for quantum mechanics was not an easy one. To resolve these problems of light and the structure of matter, we actually had to tear down much of our view of the way the world works, to a degree never seen since the introduction of natural philosophy and the modern scientific method in the Renaissance. Scientists were simply forced to construct a completely new set of principles for the physical world. These were, and still are in many cases, completely bizarre. And they are certainly very different from what our intuition, or what we might call our common sense, says that they should be. And many of these principles simply have no analogues in our normal view of reality. But we're forced to do this. If we do not do this, we actually cannot understand our world, and we will prevent the development of large areas of engineering that can create very powerful and useful technologies. We mentioned previously one of the bizarre aspects of quantum mechanics. The process of tunneling allows particles to penetrate barriers that are simply classically too high for them to overcome. This process is, however, actually nothing like the idea of digging a tunnel. There's no spade here, there's no hole that we dig, it's just not what's going on. And we're confronting here the common difficulty in quantum mechanics of finding words and analogies from everyday experience to describe quantum mechanical ideas. And we will often fail to come up with good words or good descriptions from what we see around us in our classical world as we try to explain quantum mechanics. It's not that we don't understand it, we just don't have the words to describe the things that we're talking about. There are many other surprising aspects of quantum mechanics, and as we start to learn quantum mechanics, we are confused when told, as we often will be, that some question simply does not have an answer. For example, we might think it perfectly reasonable to ask the question, as scientists did for several centuries, of whether light is composed of particles or waves. It would seem, according to our common sense, that it would have to be one or the other. But in fact, if we insist on this either-or answer, that is, that light must be definitely either a particle or a wave, then there actually is no answer to that question. The only answer we can give to it is that both of these, which is the idea of wave-particle duality, are simultaneously true. Another example is we might think it perfectly reasonable to ask what are the position and the momentum, or more loosely the speed, of some particle, such as an electron. Quantum mechanics will enigmatically reply to us that there is actually no answer to that question. We can know one or the other precisely, but not both at once. This particular enigma is an example of Heisenberg's uncertainty principle. Indeed, though it may seem bizarre, in the cases of both wave-particle duality and Heisenberg's uncertainty principle, in the quantum mechanical view of the world, there is no contradiction involved in either of these concepts. They are natural phenomena that lead to no confusions in quantum mechanics, at least if we separate them off from another and much more genuine difficulty called the measurement problem, to which we will return later. One of our natural human desires is to find causes and meanings in the things that we see around about us. These are part of the way that we construct models of reality that enable us to function efficiently as human beings. So as you learn quantum mechanics, you are likely to keep wanting to know the meaning of various terms and concepts as you work to construct your revised models of how things work. It's common and natural, therefore, for the student to ask what something means. However, I can warn you now that this is going to be quite frustrating at first. These interactions often take the following form. The student asks about the meaning of something in quantum mechanics, such as the uncertainty principle or the wave function or some other topic. And the professor or instructor replies with a question, what was it you wanted to measure? If you can tell me what you want to measure, we can figure out how to calculate that with quantum mechanics. And the student waits in vain for the professor to answer the question about what something means. This is also, and this is quite serious incidentally, called the shut up and calculate approach. Despite this, it is rather important as a student to at least try to frame these questions. Without, to some extent, fighting quantum mechanics and its ideas, you will never actually understand them properly. The more serious philosophical version of this approach is to assert that things that don't have meaning in science are the things that you can't measure, or if you can't measure them, you don't have meaning. This philosophical approach of dealing only with questions that can be answered by measurement, or that are purely logical questions within some formal system of logic, that approach is what is called logical positivism. We regard everything else as meaningless. If you can't measure it in the real physical world, it's meaningless. And it is the most common approach taken in dealing with quantum mechanics, at least at the elementary philosophical level. And by allowing university professors to dismiss most student questions themselves as meaningless, it saves a lot of time in teaching the subject. Now, one very substantial difficulty with this philosophical approach is that it is not clear in quantum mechanics what measurement actually is. Indeed, it can even be proved in at least one interpretation of quantum mechanics that you can't actually make a measurement in quantum mechanics. This whole issue is referred to as the measurement problem in quantum mechanics. And it is important to understand that the measurement problem is, in some people's opinion, really not satisfactorily resolved. You need to know that, because otherwise you may just think that somehow it is just that you are not smart enough to understand it, and that might cause you to give up. Actually, it is not clear if anyone is smart enough to understand it, so join the club. At least don't worry that somehow the problem is with you. The problem is not with you. This is a real and arguably unresolved problem in quantum mechanics. Now, if at this point you're raising an objection that there's an inconsistency in saying that quantum mechanics will only answer questions about things we can measure, but quantum mechanics cannot actually explain the process of measurement, you're quite justified in raising that objection. Now, what was it you wanted to measure? According to quantum mechanics, an object may exist in a superposition state, in which it is, for example, neither definitively on the left, in my case, nor on the right. Such superposition states are not at all unusual. In fact, they occur all the time for electrons in any atom or molecule. In quantum mechanics, anything that is moving or changing in time is certainly in a superposition state. And the idea of superpositions is actually already well known in classical physics. So many kinds of waves show what is called linear superposition, with light and radio waves being good examples in most practical situations. Waves can pass right through one another. And there's no problem with waves in thinking of the state of the surface of the sea as being one in which there's a superposition of waves going in different directions. What we were not expecting was that matter could be thought of in this way. Nonetheless, it appears that, at least in the atomic level, this idea of superposition certainly works. One kind of superposition that might happen in some systems might be that the particle, as I said, could be in a superposition of being on the left and on the right. This can happen in something like an ammonia molecule, for example, in which the nitrogen atom in that structure could either be on the left or it could be on the right of the structure. Or quantum mechanically, it can actually be in a superposition of the two. Now, though a particle might be in a superposition state, when we try to measure which state or position it is in, we always find the object is in some specific position, either, for example, definitely on the left or definitely on the right. And this almost mystical phenomenon is known as the collapse of the wave function. We might find that to be a bizarre idea, but one that, for something really tiny like an electron or an ammonia molecule, we could perhaps accept. But Schrödinger thought about this, and he proposed that we think not about an electron, but instead about his cat. He imagines that his favorite cat is sealed in a box. And inside the box there is some lethal mechanism. It might be a bomb or a vial of poisonous gas. And that might be triggered, for example, as a result of a radioactive decay. That's an apparently unpredictable quantum mechanical event involving only a single atomic nucleus. That single atomic nucleus could, quantum mechanically, be in a superposition state of having decayed radioactively and not having decayed. And in the mathematics we set up for quantum mechanics, we could view the entire system of the nucleus and the cat as being in such a superposition state. A superposition of the nucleus not decayed and the cat alive, and the nucleus decayed and the cat dead. Now, before we open the box to check on it, is the cat alive, dead, or, as quantum mechanics might seem to suggest, in some superposition of the two? Now, our experience tells us that once we open the box and look at the cat, we are going to see that it is either alive or dead, not in some superposition. So how do we get from that quantum mechanical superposition to what we see in our experience? This is actually another example of the measurement problem. And as physicists look at various possible ways of interpreting quantum mechanics, they often discuss this thought experiment. Hopefully it remains a thought experiment and that no one actually does it. For example, Schrödinger himself seems to have regarded this whole idea of his cat in the box and the superposition as showing the absurdity of what was called, and is still called, the Copenhagen interpretation of quantum mechanics, which seems to say that perhaps reality as we see it is actually created by the process of measurement, though again, it's not clear what that process is. Now, just thinking about a cat being in a superposition of being alive and dead, it seems absurd. And we cannot really check something as complicated as that. We don't know how to set up an experiment to test such quantum mechanical notions with really macroscopic objects, though people are trying to look at the idea of superposition in progressively larger objects, but they're still pretty small. One difficulty is that in trying to repeat such an experiment, we really can't set up exactly the same starting state for something as complex as a cat. So we're really not sure that the experiment is truly repeatable, and that the randomness we might appear to see in the results might just arguably be a result of the practical randomness of our different starting points in different attempts to run this experiment. Physicists disagree about the resolution of this difficulty. It is an example of a core problem in quantum mechanics. As I said, this process of measurement with its mysterious collapse of the wave function, at least in one view, cannot be explained by quantum mechanics. The proposed solutions to this measurement problem can be extremely bizarre. For example, in the many worlds hypothesis, the world is supposed to continually split into multiple realities, one for each possible outcome of each possible measurement. Now, maybe that's true, maybe it isn't, but unfortunately, as we've seen in quantum mechanics, whether or not something is bizarre is not a good guide as to whether or not it is true. Another important discussion centers around whether quantum mechanics is complete. When we measure a quantum mechanical system, there is at least in practice some randomness in the result. If, for example, we tried to measure the position of an electron in an atom, we would keep getting different results when we tried to repeat the experiment. Or if we measured how long it took a radioactive nucleus, like the one in our Schrödinger's cat box, how long it took that to decay, we would get different numbers each time. Quantum mechanics would correctly predict the average position we would measure for the electron and the average decay time of the nucleus, but it would not tell us a specific position or time yielded by any particular measurement. We are, of course, quite used to randomness in our ordinary classical world. We might play the lottery, and perhaps the lottery is decided by which numbered ball appears at the output of some machine. Often these machines are constructed with various different balls all bouncing around inside the machine, maybe driven by some air blower. And that process is sufficiently complicated that in practice, none of us can predict which ball will emerge, and all of us with our different tickets for the lottery will have equal chance. But we do tend to believe classically that if we knew the initial positions and velocities of all the air molecules and balls in the machine, we could in principle, even if not in practice, predict which ball would emerge. Those variables are in practice hidden from us, the precise positions of every molecule and atom and the velocities of them. But in a classical view of the world, we believe they exist. So behind the apparent randomness of quantum mechanics then, are there similarly some hidden variables? Could we actually predict outcomes precisely if we knew what those hidden variables were? Is the apparent randomness of quantum mechanics just because of our lack of understanding of some deeper theory and its starting conditions, some complete theory that would supersede the quantum mechanics that we currently know? Einstein believed that indeed quantum mechanics was not complete, and that there had to be some hidden variables that once we understood what they are in this deeper theory would resolve quantum mechanics and remove its apparent randomness. Relatively recent work centered around a set of relations called Bell's inequalities shows, rather surprisingly, that there are no such hidden variables, or at least not what we call local ones that propagate along with the particles. And that despite its apparent absurdities, quantum mechanics may well be a complete theory in this sense. It also appears, even more strangely, that quantum mechanics is non-local. Now, what do I mean by that? Two particles can be what's called entangled, which is actually a concept made up by Schrödinger in discussing all of this. They can be entangled quantum mechanically to such a degree that measuring one of them can apparently instantaneously change the state of the other, no matter how far away it is. Now, whether you regard this as a cause and effect is actually not at all clear, but still is an aspect about this that seems to happen as if there were cause and effect. It is certainly the case that it's not possible to use this phenomenon to communicate information faster than the velocity of light. This non-locality is very odd, and it's often known through the original, what is called the EPR thought experiment, or paradox, that was proposed by Einstein and his colleagues Podolsky and Rosen. And incidentally, it was apparently discussion of this paper between Einstein and Schrödinger that led to Schrödinger's discussion of his cat, and as I said, also his introduction of the concept of these entangled states. So this is a very strange idea, one that we are, as scientists, still grappling with, this idea of non-locality. But it seems that maybe quantum mechanics is complete as we stated it, and maybe there are none of these hidden variables, which leaves us with some very bizarre conclusions. Despite all its absurdities and contradictions of common sense, and despite the initial disbelief and astonishment of each new generation of scientists, of students, about how quantum mechanics works, as far as we know, it is never wrong. We have made no experimental measurement that is known to contradict quantum mechanics, and there have been many very exacting experiments. Quantum mechanics is both stunningly radical and remarkably right. It is really an astonishing intellectual achievement. The story of quantum mechanics itself is very far from over. We are still trying to understand exactly what are all the elementary particles and just what the implications of such theories are for the nature of the universe. Elementary particle theory we will not get into in this course because it requires relativistic approaches, and we will leave those for later and we will not make them part of this discussion. However, many researchers are working on the possibilities of using some of the strange ideas in quantum mechanics for applications in handling information transmission. One example would send messages whose secrecy was protected by the laws of quantum physics, quantum mechanics, not just by the practical difficulty of cracking classical codes. Another example is the field of quantum computing, in which quantum mechanics might allow us to solve problems that would be too hard ever to be solved by any conventional machine. Now, at this point, you may be feeling overwhelmed by all of these strange ideas and be about to give up in despair. How can anyone ever understand such a bizarre theory? And if you can't understand it, how can you even think about using it? Here is the good news. Whether we think we understand quantum mechanics, and whether there is yet more to discover about how it works, quantum mechanics is actually surprisingly straightforward to use. The rules and the approaches for using quantum mechanics in a broad range of practical problems and engineering designs are relatively straightforward. They use the same mathematical techniques that most engineering and science students will already have mastered to deal with the classical world. And because of a particular elegance in the mathematics of quantum mechanics, namely that it is based entirely on linear algebra, quantum mechanical calculations can actually be easier than those in many other fields. The main difficulty that the beginning student has with quantum mechanics lies in knowing which of our classical notions of the world have to be discarded, and what new notions we have to use to replace them. Indeed, it is this aspect that makes it very difficult to teach yourself quantum mechanics. Because such basic conceptual shifts are required, you simply can't pick up quantum mechanics just from encountering bits and pieces of it as techniques here and there. You really need to take a course that forces you through a fairly complete development of the subject's concepts. As you do this, you should expect to spend some time in disbelief and conflict with what is being asserted to you in quantum mechanics. That is entirely normal. In fact, a good fight with those propositions is probably psychologically necessary if you're ever to get on top of the subject. Incidentally, I should say that the associated teaching technique of breaking down the student's beliefs and replacing them with the professor's correct answers has a lot in common with brainwashing. And as we mentioned above, there is a key point that simplifies all the absurdities and apparent contradictions. Provided we only ask questions about quantities that can be measured, there are no remaining physical problems that need worry us, philosophical problems. At least none that would prevent us from calculating anything we could measure. As we use quantum mechanical principles in tangible everyday applications, such as electronic or optical devices and systems, the apparently bizarre aspects of quantum mechanics simply become commonplace and routine. You may soon stop worrying about quantum mechanical tunneling and Heisenberg's uncertainty principle. Perhaps in the foreseeable future, such a routine comprehension and acceptance might also extend to concepts such as non-locality and entanglement as we start using those more in practical situations, for example, in sending secure information. For any of us, understanding quantum mechanics marks a qualitative change in our view of how the world actually works. That understanding gives us the opportunity to apply this knowledge in ways that others cannot begin to comprehend. Whether your goal is basic understanding or practical exploitation, learning quantum mechanics is, in my opinion at least, certainly one of the most fascinating things you can do with your brain.